Hi, we are continuing the discussion for Chapter 4, Transistor Theory, and we will, in this lecture, discuss non-ideal transistor behavior issues. And before we get there, let's explain one thing, is that in terms of um, transistor behavior and features, it is clear that um, if we have the feature size or transistor length greater than quarter a micron, typically what we have studied applies, and this is referred to as long channel transistor. Okay, and what we have derived in terms of equations are applicable for transistors, but this is unfortunately old technology, right? This is old technology, and nowadays most of the or probably all of the electronic devices that are being manufactured are of feature less than quarter a micron or 250 nanometer, and these are referred to as short channel devices. Um Channel devices, and these are the recent the devices that are amongst or are being manufactured right now. But these devices, they deviate from the features that we have derived, and they kind of exhibit some kind of non-ideal, okay, behaviors, and this is what we will study in this lecture. Okay, all right, so um, uh, so these are the list of non-ideal behaviors. The very first we're going to discuss is the high field effects that we will examine. Okay, so typically what one of the things that triggered uh, scientists and engineers to look at some of the non-ideal behavior was the behavior of the current in short channel devices. You see, in the black here is what we expect from the derived equations, and in the blue is the behavior of these short transistors. And so engineers and scientists were some kind of baffled as why we have this drop in current of what we expect versus what we see, and they attributed this droppage in current to velocity saturation and mobility degradation, and we will define those. So basically what they cause is reduction 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 in current. And is this good or bad? Of course bad. Current for circuits is like blood for humans. So less of it is bad. So we were not happy to get less of current. And basically this is the problem: velocity saturation and mobility degradation. Now, of course, here, this is showing off in the saturation and the off current. But let's just go to the definition right away. The This is basically this velocity saturation and mobility degradation results from high field effects. High field effects. What do we mean by high field effects? If you look at the transistor, okay, and so this is the source, this is the drain, okay, and you have here the SiO2, and then you have this is the gate here. So you will see that there is the vertical electrical field, which is basically what attracts the charges here and form the channel. And then you have the lateral electrical field, basically, which pushes the charges from the source to the drain. Now, when distances reduce and when we make these devices smaller and smaller, the L and the TOX gets smaller and smaller, and this electrical field, which is the result of dividing voltages over this physical distance, increases dramatically. so much so that you reach to very high values that the current, the behavior of the device starts to deviate. So in the lateral, we call the lateral electrical field, which results or estimated by dividing VDS over L. This is where it moves the electrons and holes, okay, across the channel. Typically in ideal transistor, the carrier velocity changes linearly with the lateral electrical field. But in short channel devices, this relation does not apply anymore. It's no more linear, so it ceases to exist. And when the carrier velocity is no more linear with the lateral electrical field, we call this velocity saturation, and this is a result basically in less of a current. Okay. Then the second electrical field, which is the vertical electrical, which is in charge of forming the channel, which is expressed as VGS divided by TOX. The carriers unfortunately scatter off the oxide interface, which is right here. This is the oxide interface, right, where the oxide touches the surface of the silicon, and therefore slowing the progress of the carrier, and that reduces the mobility of the carrier, and that's what we refer to as mobility degradation. And it basically reduces the amount of current. Of course, that happens at high values of VGS. Okay, so uh, one electrical field in charge of moving the carriers, another electrical field is in charge of creating the layer of the carriers. Both of them at high values of those electrical field exhibit those deviation we call mobility degradation, velocity saturation. The net effect is less of a current. Let's go into more details now. Okay, so basically, just to sum up what we said, vertical electrical field is basically VGS over TOX. It is in charge of forming the channel, okay? And in long channel or in ideal behavior devices, we have seen that the charges on the channel are proportional to the electrical field. Now, in lateral electrical field, which is expressed as VDS divided by the length of the channel, it accelerates the carrier from the drain to the source, and typically the velocity of the carrier is linearly, the velocity of the carrier increases linearly with the lateral electrical field. And when that ceases to exist, then we say that we have velocity saturation. Okay? Yes, velocity saturation. All right. Now, let's talk about what happens during mobility degradation. And basically, mobility degradation, the increase in VGS causes the mobility of the carrier, whether it's an electron or a hole, to reduce. And there is really complex analysis behind it, but this collision with the oxide interface basically reduces the mobility of these carriers, and folks try to estimate this for the electrons and the holes, and they came up with this expression. Notice where the VGS is situated here, basically ended up reducing the effective mobility and for both the electron and the holes. And therefore, one of the things that you might see in your assignment or exam is compute the effective mobility for an nMOS and PMOS transistor when they are fully on. Why when they are fully on? Because this is where you have the maximum VGS, okay? This doesn't happen when the device is off. So now for the nMOS transistor, okay, we plug in 550 square centimeters per volt per second. Okay, this volt here comes in, and we apply a VGS of 1, VT of 0.3 volt, and you plug in these numbers and you come up with 96, and obviously less than the ideal mobility. Less mobility means what? It means less current. Why? Because basically the speed of the carrier, which is the electron, equals the mobility times the electrical field. Okay, and similarly, we compute the effective mobility for the holes, and you can see similar formula, but make sure you use here positive values for the VT and the VGS. Okay, all right. Now, um, again, notice the mobility for the holes are degraded here. Okay, so this is the mobility degradation. Another factor we mentioned before is the velocity saturation. And velocity saturation, basically, we say that typically carrier velocity increases linearly with the lateral electrical field. And unfortunately, the carrier scatter of atoms in the silicon lattice, and that causes the velocity. Of course, that happens in high electrical field, and that results in less of the velocity of the carrier. And here we are plotting the velocity of the electrons versus the electrical field here, and you can see that we kind of get this nice linear behavior in the beginning, and this is for the electrons and these are for the holes. Then you get this bending here, and this is what they refer to this is when the critical electrical field starts for both for the holes and the electrons. So the critical electrical field basically is where we start seeing this relationship ceases to exist. Basically, we are not increasing the velocity of the carrier linearly with the lateral electrical field, and we can that's why we can estimate the velocity of the carrier both for electrons or holes as mu effective times the electrical field divided by the electrical field divided by the critical electrical field plus 1. This applies as long as I am less than the critical electrical field. Now, above the critical electrical field, the velocity saturates and we get V Sat. What's the value of the critical electrical field? It is 2 times V Sat over the mobility, effective mobility. Okay, now we know that the electrical field equals the volt over the VDS over the channel length. So where is this critical electrical field? Well, it happens when I get the the critical or what's the critical voltage, critical VDS voltage, which triggers the critical electrical field. Well, it is the critical voltage happens when I get the critical electrical field, and this is the value of the critical electrical field times the channel length. You get the critical voltage. This is the critical VDS voltage, which triggers the phenomena of the voltage saturation. I'm sorry, velocity saturation. Okay. All right. Now, here is another example you might see in your assignment or quizzes. For example, we say find the critical voltages VC. Okay. For fully on nMOS and PMOS transistors using the effective mobilities from example, which is the previous example. Basically, previously we said that from the previous slide, the critical electrical field equal to V Sat over effective mobility, and also the critical electrical field from this equation equals the critical voltage divided by L, right? So all of these parameters are here, right? Except this critical voltage. So I substitute for those parameters, and I find the critical voltages for the electron, and I find the critical electron voltage for the holes. Okay, all right. Now, because of velocity saturation here, these nice current where we have these quadratic relationship in which the current increases quadratically with VGS over T, they kind of cease to operate. And now we have a new functions, right? And so people try to find out those new functions, and you can see this is one of the functions that we estimate those with the non-ideal behavior. And you can see that the VGS here is of linear in relation linear relation with the IDS. Some folks would like to express now IDS in relation with VGS in terms of alpha, the power alpha, where alpha and the rest of these parameters kind of estimated empirically from the plots that and which are the results that engineers measure in the lab. And this alpha is somewhere between 1 and 2. Okay, but it's never reaches 2 because we don't get to the ideal behavior right now. The end result of all of this is what is we are getting less current or IDS current because of this velocity saturation and mobility degradation. Okay, that's the main message here. Okay, then we have other effects, non-deal effects, like the channel length modulation and the other effect like a drain induced barrier. By the way, the channel length modulation, both this is caused by the VDS voltage, but this is the channel length modulation is caused by the VDS when the device is on and in specifically in saturation, and the drain induced barrier impacts the device which is off, and basically basically what it does, it reduces VT, the threshold. So channel length modulation is caused by VDS when the device is on. Drain-induced barrier lowering, it's also caused by VDS, but the device is off, and it reduces VT. Basically, it reduces VT slightly. Okay, and the body effect, it is the V source body. When it increases, it tends to increase VT as well. And short channel effect says that when in short channel devices, when we increase the length of the device, we increase the VT of the device. So we will go over, this is some kind of quick summary here, but I'd like to sort of like show you the relationship. These last three, they impact the VT, the threshold of the transistor. But notice channel length modulation and drain induced body lowering is caused by VDS. Okay, and one on the when the device is saturation, one in the device is off. Okay, so okay, I think I said that verbatim. So let's go and okay. So channel length modulation, what it does is basically if we recall the current relationship with VDS, we say that the current somewhat goes like this, and when it reaches saturation, it flats. What people found out that this is not really flat when we reach this. It turns out that the current increases slightly when we are in saturation. So this is basically the saturation. This is basically the saturation. So this is the saturation. This is the saturation region. This is the linear, right? So the current slightly increase, and it increases in linear with VDS, but with a small amount. To emulate this behavior, we kind of go back and modify. You see, this is the function that we know of for saturation. Then we go back and says, no, 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 we need to add a factor here. We need to multiply this equation with 1 plus lambda VDS. Now, this lambda is not the same lambda we use it for feature size. It's some kind of different lambda, very small. Sometimes it's about 0.1 to 0.09, etc. Okay, very small, but it gives this slight reward in current for slight increase in current as we increase VDS. Okay, now why this happens? Well, with high value of VDS in saturation, the width of the depletion region, which is right here. This is here the drain. This region is the drain. There is this depletion region here, okay, around the drain, and this depletion region, as you increase VDS, it increases. And I know that L effective, which is the L effective for the channel, it is L minus LD. As you increase VDS, this LD increases, and thereby reducing the effective length of the channel. And when we reduce the effective length of the channel, the current tends to slightly increase. Okay, so so it's because the depletion region grows in the around the drain as you increase the VDS, causing the L effective to reduce, causing the current to. Remember, this beta here has a term which is W over L. So if this is reduced, then beta will go up, and then IDS will increase as well. Okay, so this is the channel length modulation, which basically says that the current in saturation increases slightly because of the increase in the depletion region around the drain. Okay, and this happens when the device is in saturation. Okay, now the effect on the threshold voltage, um, we say there are three effects: body effect, drain-induced barrier lowering, and short channel effect. In terms of drain-induced barrier lowering, it's one of those, again, one of those that is caused by VDS. So VDS when the device is off, so the device is off, right? A high value of VDS tend to decrease VT. And again, why it decreases is because as you increase VDS, the depletion region around the drain increases, and thereby some kind of we need less number of charges to form the channel. Effectively, we are making the voltage that established the channel lower slightly. Effectively, we are reducing VT. Okay, so that's basically what happened at high drain voltages. Um, um, so basically, it does happen for the device when it is off. Now, drain induced barrier lowering, it affect the we will study in the next lecture the leakage currents. And the leakage currents, those are the currents that happen or that are leaked by the device when and one of them, the subthreshold current, when it's an off state one, we see that the DIBL, which is the drain induced barrier lowering, increases the leakage current. Okay, but let's stay here, and we know that VT will be reduced for the off device by the increase of VDS. Okay, body effect, it simply says that as we increase the source to body voltage, right, the VT does increase as well. Okay, so the formula for this is that people found out if we increase the body, I'm sorry, the voltage between the source and the body, then VT increases with this formula. So it's a square root of the potential, surface potential, which is this one, plus VSB minus the square root of the surface potential multiplied by the body effect factor plus the VT, which is the ideal VT, which is when VSB equals 0 volt. Now this gives me the effective VT, and as VSP increases, notice as VSP increases, you will notice that this term does increase, and which eventually leads to the increase in VT. Okay, the surface potential is estimated as 2 times VT. Well, this is not the VT, which is the voltage, and logarithm of the doping level over Ni, and the body effect is estimated with this expression. Now, typically, here's a question you might see in your assignment or exams that it says consider nMOS transistor 65 nano process with nominal voltage is 0.3, that is our VTO. How much does the threshold change at room temperature if the source is at 0.6 volt instead of 0? So that means VSB equals 0.6 volt. Now, the very first thing, we need to compute this formula, but we know that we need the body effect to be computed. And for the body effect to be computed, and then we need also to compute the surface potential. So we compute here the surface potential, and it comes out to be 0.93 volt, and we compute the body effect, and it comes out to be 0.16. Then we plug in everything in this formula, and we get 0.34, which means the VT, which means in this example, when we raised VSB from 0 volt all the way to 0.6 volt, VT gone up from 0.3 volt all the way to 0.34 volt. So 0.04 increment in VT. Okay, short channel effect basically in small devices. Okay, if we plot the VT with the length, so we kind of see this kind of behavior, and as you increase the L, the VT slightly increase. Again, all has to do with the dynamics of the depletion region for the source and drain, and the larger the feature is, or the larger the L is, we are some kind of away or less impacted with these depletion regions, and thereby giving the VT higher values. Okay. All right, I think with this, I'm going to stop here, and we continue the discussion of the feature of the non-ideal behavior in the next parts of this lecture. Thank you.